All right, last time we were together, we started with section 1.1, and we were looking at differences between how calculus and pre-calculus treat topics and what they can do. And I believe that we were on this one. Does that look right? Haven't seen that one yet? Okay. All right, so this information is information that shows up in Calc 2. So we're not going to spend a lot of time talking about it, but there are differences, and you'll notice it's very much like what we were just discussing last time. The things you see in the left-hand column are very rigid shapes, right? They have a definite equation or formula. And then the things that you're seeing on the right-hand side are variable. They have flexibility. They're curved, or in the case of the second one, it talks about a variable density, right? Density is how heavy something is at a particular point in the object, right? How thick or weighted it is. Also, you see down here at the bottom, sequences. This is Calc 3 stuff. So over here, finding the sum of a certain terms, if I told you to add up the numbers from 1 to 100, you could do it. You might not like it, but you could do it, right? But if you're supposed to add up something that's infinite, you can't do that with pre-calculus. You need some other techniques, and that's a calculus topic. So, was that my last one, or did I skip one? That was the last one. Okay. All right. Well, then we're ready for some examples. So these are two very specific examples, how you can see calculus versus pre-calculus used in a topic. So this is the first one. This is a tangent line problem. So the tangent line problem, we saw an example of this in that list, and it talked about being able to find secant lines with pre-calculus and tangent lines with calculus. Secant lines, if you'll remember, cut through an object, and tangent lines just touch an object and sort of bounce off. So a secant line for my circle would look like that. For my object over here, it would look like that. Those are secant lines. I'll change the color, and we'll do tangent lines. So let's go with purple. Tangent lines touch at only one point, so maybe they just touch at this very tip top right here. That's tangent line. Or over here, they touch just over here at this very, that's not a good one. We'll go with that very tip point over there. So it's like here and here. So those are tangent line problems. So what I'd like to show you is how we can use pre-calculus to estimate something that calculus will later on tell us in a much easier way. So the whole goal is for you to appreciate what's coming next, because this is really annoying. Got that? That's really it, right? It's just really annoying to do it this way. It's doable, super annoying. So the idea with the tangent line problem is, let me draw a line here for us. Okay, so in pre-calc, we can find the slope Is that big enough for where everybody's reading? Is it okay? Okay. To find the slope of a secant line, we can use 2 points on a curve and calculate the slope between them. All right, back to where we were. You can calculate the slope between them. And you know how to do that. You calculate slope by taking I didn't mean y equals, by taking the change in the y values, so y2 minus y1, and dividing it by x2 minus x1. And if we have, we're just going to draw an arbitrary curve, put it on axes. So if we have 2 points that we're trying to find the secant line between, say here and here, we would then have an x value and a y value at each location. So this will say is x1 and y1, and this one over here is x2 and y2, and we could calculate that, right? Yeah, we could totally do that. So what happens though if we don't want both of these points and we only want this point over here on the left, just this one that says x1, y1? That's where we want it to be. We want it to be a tangent line there instead. Okay? That's sort of where we're headed with this. And this is the general idea. So in calculus, we can find the slope of a tangent line. We do this by using secant lines. And let our points get closer together. So we're going to take this same picture that I have over here on the left, and we're interested, because I've chosen it, right, in this point x1, y1. We're going to try and find the tangent line there. And so what we do is we take the point where we are, which was at x2, and we just get closer to the point where we care about. So we move in closer over here and we draw this tangent line. And secant line, excuse me. And then we say, okay, well, I want to get closer than that. And so we get closer than that, we go over here and we draw this secant line. Sorry. And the point that we're calling x2, y2 keeps getting closer and closer and closer to the point we care about, x1, y1, until we're practically there, right? That's the idea. So that's called a limit. We're letting the distance between them get infinitely small. We're letting the points get infinitely close together. That's a limiting process. Now, we don't really want to calculate all those slopes. We're going to do it today. But after today, we're going to start looking at other ways that we can find similar quantities without that much work, okay? But this is a calculus idea, the idea of letting these things get infinitely close together. The area problem is another one that we're going to encounter. This is in chapter 4 of our book, where we're going to get to, not do it the hard way. But let me show you what the idea is if we were to try to do this idea with pre-calculus. So in the area problem, which we talked about last time, in pre-calc, we can find the area of certain shapes. Rigid ones, right? Ones that have definite formulas, things like rectangles, triangles, even ones that have definite formulas that aren't rigid, like circles, right? They have a defined formula. And we can do better than that. I mean, there's lots of shapes we can find area of. They just have to have a specific form, right? They can't just be variable, okay? So when we do this, we have formulas that have been developed that we use. Right, so for example, if we were doing rectangle, we talked about this one last time. You guys even gave me 2 different formulas for a rectangle's area. One of them is base times height. The other one, sometimes people call is length times width. Right? There's a formula, and you can use it, and you do this in middle school for the first time. You do more of it in high school. This is pre-calculus ideas. Okay? In calculus, we can use the areas of rectangles to find the area under a curve. And here's the way it looks. So I'm going to draw that same kind of a shape that I had before because it's just a good vague shape that we're going to use. And let's say that you wanted to find the area, and I'll shade it in, and then I'll delete it. That one. The area right here. And we were interested in finding all of this area. Okay, that's our goal. We want to find the pink stuff. Okay, so what do? Well, we split our shape into 2 boxes, and then we split it into 4 boxes, and then we do it into A boxes. You do infinitely many boxes here, and you find the area of the rectangle created by each box. So some of the rectangles end up being overestimates, like this one, and some of them end up being underestimates. The over, the under depends on which side you use as the height, depends on what the equation of the curve is, that kind of stuff. But can you imagine what would happen if I took this shape and I made twice as many rectangles? The overages and the underages, that's not a real word, but pretend for a minute, of all of my shapes, areas, they would get closer to the shape that was in pink to start with, right? And if you did this infinitely many times, right, this idea of doing things infinitely many times, you'd get really, really close. Close enough that you'd be good with the answer, right? You'd call that your answer. And it's really important to notice that when we get to the point of doing some of these calculus concepts that are finding exact answers for us, your calculator's doing this, which means sometimes your calculator is slightly wrong and you're smarter than your calculator is. Shocker, right? Please go tell everybody you are smarter than your calculator. You are. It can't do what we're going to do. It's going to do this stuff every single time. All right, so let's look at some examples, and these are the ones that show up in your web-assigned homework, of trying to decide when we can use pre-calculus and when we can use calculus to do a concept, and if we're going to use calculus, how we would approximate that and do it. So the directions ask to decide which of those we're going to be using. If it's calculus, explain why, and to use a graphical or numerical approach to estimate the answer. So, consider the equation. F of x equals 4x plus 3. What is the slope of this curve at x equal to 2? Now, just because it's asking you for slope does not put you in either category, right? Over here, we found slopes in both categories. But one is asking for a slope that's related to a calculus concept and one that's related to a pre-calc concept. So what we have to decide is, what is this an equation of? And what is it an equation of? A line. A line is very rigid. You know how to find the slope of a line. In fact, there's no calculation necessary here at all. The fact that they told you that the point is at x equals 2 is completely irrelevant. Are you with me? What's the slope of this line? 4. Why? Yeah, it's in slope-intercept form. You can see it, right? So this is definitely pre-calc. And the real reason it's because it's a line. So you might want to actually write yourself a note here that that's the why. It's a line. If I had an equation that was a curve, we couldn't do that, right? In fact, we're going to see that on the next example. This is a line, and its slope is always the same. It slopes 4. So the problems that are pre-calc are really fast, really easy to do. Problems that are calculus are going to be tedious and annoying. Okay? They just are. So let's take a look at the next one, because it's going to be calculus. What makes this calculus? It is not a line, right? It's a parabola, or it's a quadratic, right? Yeah, that makes this calculus. And it's not going to be as easy to do. So this one is calculus. And it is because it's not a line. If you want to be more specific and tell me what it is, that's great, but it's not a line. So I want to show you how you would go about doing this with numbers to actually find the quantity that we're looking for. Okay? So our value x equal 2 here now matters because it's curve, and curves have different slopes at different points, right? If you run up hills, you know this. The hills are steeper at different points, aren't they? Right? So that's what's going on with our curve. So we're going to take a look at your calculator to do this. So go ahead, if you have your calculator with you, go ahead and grab it. And I'm going to be flipping back and forth between this image and the calculator image. Oh, we're just going to see what happens. I say I'm going to. There's a QR code. That's exciting. All right. Okay, so change plans, we're going to use our calculator, but I'm just going to have to guide you through how to do it. All right, first of all, x equals 2 is that x1, y1 point that we talked about for my picture, right? The one that we said we're going to leave steady, we're not changing it. Everybody good with that? But we want points that get closer and closer to 2. All good? So we've got a table set up on purpose. There's 2 columns. One of the table's columns are going to be values that get bigger, that are bigger than 2 and get closer. The other one is going to be values that are smaller than 2 and get closer. So these are the points that I recommend. WebAssign will choose points for you, so you don't necessarily get to pick your points there. But 2.1, 2.01, 2.001. Those are values that are bigger than 2, and they get closer. Everybody good with that? Okay? We're going to do the same thing on values that are smaller than 2 and get closer. We're going to start with 1.9. What do you think the next one might be? 1.99. And the third one? 1.999. Okay? These are the x values. Now, if you have an x value, you can find the corresponding y value. You just stick it in the equation, right? No problem. So we need to do that next. So grab your calculator, and I want you to take each of these x values, 2.1 all the way down to 1.999, and put it in the equation, 3x squared plus 2x minus 4. Okay, if you have a graphing calculator, I can show you how to do that really quick and easy, where it gives you all those answers fast. If you're using a scientific calculator, you got to enter them one by one, and it's kind of tedious. Okay, so I'm going to give you instructions, and then this way too, if you're not having a calculator in class today, but you have it later, you can come back and listen to these instructions and follow through. So I want you to hit y equals. Clear out anything that's in the y equals prompt. So your screen should say plot 1, plot 2, plot 3 across the top. They should all be just like written there with no boxes around them. Underneath it should say y1, y2, and so forth. Does anybody's screen not say that right now? It says something different. Okay, great. We're going to put in 3x squared plus 2x minus 4. Okay, all good? Next step, and this is the one that you usually have to change something unless you've played with your calculator and done some of this before. I want you to hit table set. So table set is underneath the window button. Window's along the top. The way you get to the table set is you hit the second button and then the window button. Okay, the second button is in the top left-hand corner. It's usually a different color on my screen. It's a kind of a yellowy orange. Second, window. And you get a screen that says table setup. Okay, so anybody who has a calculator not in the table setup screen, you don't see that on yours, you muted that. Okay. Inside a table setup, the independent variable, it says independent, dependent. The independent variable needs to say ask. The dependent variable needs to say auto.
Does the table start?
Doesn't matter. It won't affect anything that we're doing. So table start can say whatever it wants to say. Doesn't matter. What we're doing is we're telling our table that we don't want it to pick the values that we're putting that it has adds in there, we want to pick them ourselves. And then that will allow us to pick these 6 values, which means we can get the answers very quickly. Okay? Now, if you actually go into table, so press the table button, which is second graph along the top, it's the far right button, second graph, you now have a table. Mine has stuff in it because I've used my calculator to do this before. If yours has stuff in it, just press delete on all of the little entries and they'll delete out one row at a time. At that point, I have an empty screen. So my screen looks like this. Okay? So everybody's screen kind of look like that. Come over that direction. So you have an empty screen, empty columns. It says X, it just should say X and Y at the top though. X and Y1. Okay, does anybody's not look like that? Okay, now we can put in 2.1, 2.01, and so forth. Now, when I do that, what I'm finding is the f of x values here. I'm getting y values out of this equation. So I'm going to fill mine in the table. I have 13.43. You want as many decimals as it shows to 6. Okay, you're wanting to show lots of decimals. Also, if your screen truncates it, like for example on, I'll write them down. Actually, the first 2 are fine. So 12.3414. My third one actually says 12.014, but it's hard to tell if it stops or if it just ran out of space on my screen. If you arrow over it, just like on the cursor, use the cursors to move over on top of it, it will tell you a longer value, like more accurate at the bottom of the screen. So at the bottom of my screen, mine actually says 12.014003. Okay, so that's what I want, is I want all the decimals that it shows up to 6. Okay, are we good? We're going to do the same thing in the next column over here with the 1.9s. Okay, so these are the values that will come out. If you're using a scientific calculator, you can just enter them in one by one, right? You can actually put in 3 times 2.1 squared plus 2 times 2.1 minus 4. You can put each of them in independently. It just takes it a little longer to calculate everything for you. That's already kind of a lot of work, just finding the y values, and that's not really what we wanted. We want the slope. How do you find slope? Well, we wrote the formula before. y2 minus y1 over x2 minus x1, right? But in every single one that we're about to do, we have x1 and y1, or at least we almost do. We have x1 anyway. What's the x1 value that we're going to stay fixed the whole time? 2, yeah. So that's going to be a 2. I don't actually have the y1 value given, but can I find it? Sure. You can just put it in the table too, right? We didn't do it, but we could. It's 12. So on every calculation that I make, I'm going to have a 12 and a 2 in these locations. So I'm going to calculate 6 slopes. How do I do that? Well, I'm going to go in one by one, and I'm going to use the values that are in my table. So the first one that's in my table, the first y value is 13.43 minus the 12. That's going to stay the same every time, over 2.1 minus 2. So this is my first slope value. We'll call it M1. And my calculator will do that for me, right? This is one of those things like, calculator is quite useful at this point. We don't want to do that by hand. You might have been able to do the other stuff by hand, but at this point we don't want to do that by hand. So you've got 13.43 divided, or minus 12. And you're going to end up dividing by 0.1. And I got 14.3. Is that what y'all's got? Your calculators, yeah? Okay, good. So this one's 14.3. And my slope here is 14.3. And now I do the same thing. Uh-oh. That's not what I meant. But I'm going to make some changes, right? I want this to be M2, and I want this to be 2.01, and I want this to be 12.14. It's 1403. I didn't get that finished writing when I was doing it before, so sorry. And I'll let my calculator calculate that again. 12.1403 minus 12 divided by 0.01. And this time I have 14.03. We're going to do this how many times? 6 times. Okay? So I'm going to just beg your pardon and not write all 6 of them down. Do you think we're okay with seeing what we're doing? Each time, all we're doing is we're changing this part of, I should use a different color highlighter. Let's try that. Blue's good. There we go. Every time we're just changing the x1 and the x2 and the y2. We're leaving the x1 and the y1 the same, and we're calculating a new slope every single time we do that. Now, when we do that, we get 6 different values, and you start to notice a pattern in those 6 values. So let me just stop here with those 3. If you're going down this column, what does it look like it's getting close to? 14, right? Okay. Now we got to do it from both directions, and that will be clear later when we get to, I think it's section 1.4, why we need to do both directions, but we do. On the other one, we're going to get 13.7, 13.97, and 13.997. And as we go down this column, what's happening? It's also close to 14. And because they match, right, then we can actually say that the slope we're looking for here, we're expecting it to be 14. At the very least, it's approximately 14 from what we found. And that's how we would approximate the slope using calculus. And that's a lot of work, right? It is. Chapter 2 is going to be like the light bulb moment. We're going to be like, oh my goodness, why do we have to go through chapter 1? To make you appreciate chapter 2, okay? So it'll be all right. But this is the way it works.